Okay, so we'll get back to those graphs in just a moment. So remember that when you did your reading in the preface of the book, we had a quiz about this, top hat quiz. We said that calculus is really about two goals. All of calculus boils down to one of the two things. You know how much of something you have, and you want to know, so we could say, you know how much of something you have at every moment. And you want to know how fast it is changing at every moment. Okay? That's goal number one, or goal number A. And then goal B, you know how fast something is changing at every moment. And you want to know how much of it you have at every moment. Okay? So that, all calculus, what we work on all semester long, really boils down to one of these two things. So with everything we've done so far, we're ready to begin endeavor B. So the next 3 weeks or so, we're going to be working hard at this endeavor B. You know how fast something is changing at every moment, and you want to know how much of it you have at every moment. So what is it that we would have that we would know how fast something is changing at every moment? What would that be? What would that be that we know how fast something is changing at every moment? Rate of change function, right? A rate of change function. That's what tells us you know how fast something is changing at every moment, okay? So you had this. Oh. This is what you should have, okay? The rate of change is constant. No matter how much time has gone by, you still have a 1.5 gallons per minute. That's your rate of change. And most of you eventually ended up there. Many of you got it right at the beginning. Okay? So, in this endeavor, you know how fast something is changing at every moment. You want to know how much of it you have at every moment. What is that thing that we would have? We would have this. We would have a rate of change function. That would be given to us. What? It tracks the rate at which a quantity changes. Okay? So this is like an example. Very simple, right? Just a constant rate of change the whole time. But it's an example of a rate of change function. It's what we would have if we were on endeavor B. And then we want to know how much of it we have at every moment. So there's two kind of that are very similar ways to represent that. First is, when we talked about the number of gallons added, that's what we're going to call a net accumulation function. The number of gallons added in this example is an example of a net accumulation. What does it do? It tracks the amount of change since you started. That's what the y value is in a net accumulation function. It's the amount of change, total amount of change, since we started whatever our initial was. In this case, 0. That's a net accumulation function. So that's one version of knowing how much you have at every moment. Okay? Another version of knowing how much you have at every moment is very, very close. These are like cousins. Would be a total accumulation function. And what's the difference with that? That tracks the total accumulation of the quantity. So you would include any accumulation that happened before, right? So we already had 2 gallons in that tub, so that counts as accumulation, as total accumulation, and then we start adding more. So then the total accumulation function is telling you the total amount of accumulation at any given value of the independent. So both, and so they're almost the same, right? That how is the total accumulation different from the net accumulation? Just all the y values or all the amounts are just 2 greater, right? So it's just the total amount that you have is always 2 greater than how much has been added, right? How much has been added. So these are almost one and the same. We definitely want to make the distinction, but both of these are, ways to say this is how much we have at every moment. Either how much change we've had or how much total accumulation we've had. Okay, so really important. So we're getting our language down. So our endeavor in the next 3-4 weeks is going to be, we know how fast a quantity changes every moment. In other words, we have a rate of change function. And from that rate of change function, we want to recover or build either a net accumulation function or a total accumulation function. How much we have at every moment. Okay, so this is the journey and this is now, we're on the journey of calculus now. We've got all the building blocks in place. Constant rate of change, and now we start delving into the calculus. Okay, so if you flip over your page, okay, so this function, R sub V, it gives the rate of change of volume of oil expelled per day by a rig that begins leaking at t equals 0 days. Okay, so an oil rig starts to leak, and then we're going to call that t equals 0. And then this function now is, we have a graph representation of this function that's giving us the rate of change. The rate of change of oil leaking in meters cubed per day at any number of days since it started leaking. So can you imagine a function? So you're gonna leave yourself some space, but if you want to take some space to maybe sketch, could you imagine the function v that gives the total amount of oil expelled? Okay, the total amount of oil expelled. So what is that? So in this case, at day 0, there was 0 oil accumulated, right? So the net accumulation function and the total accumulation function will be the same. Does that make sense? Since there was 0 at time 0, the amount of change is going to be equal to the total amount accumulated. All right, so there's only really one accumulation function we need to talk about here. So can you imagine, maybe make a sketch of what that would look like based on this rate of change? Can you sketch the accumulation of oil as a function of days in the ocean? See if you can do it. Yeah. So over to the right, it's like over to the right, not below. You're probably going to need the space below for something we're going to do. So maybe over to the right somewhere. Sketch what the accumulation function would look like. And here, net accumulation and total accumulation are the same. I just want to glance and see which way. What do you think? Accumulation of oil in the. Okay, so that's the good ones. Compare with the person next to you, so you can come up with the same thing. What's always true about the rate of change? What's always true about that rate of change? What's always true about that rate of change? Positive. That means what about the accumulation? Increasing, right? So when you see this, is the amount of oil in the ocean going down? No. The rate is positive all through here, so it's always going up. So what's happening here? It's still going up, but just the slowest, right? It's still going up, but this is the slowest that it's going up. So I saw lots of good graphs, so maybe something like this. Right? It's going up the fastest at the beginning, and then the amount of oil increases the fastest at the beginning, but it keeps going up, just going slower. So that's what we said. The slowest that it increases is around 1.3 days, say. But then that rate speeds up again, and that's seen that way. Okay, so if you had just something like this, but the key is that volume of that accumulation of oil is always increasing. Why? Because the rate is always positive. So our endeavor will be to develop the quantity function like V. So this is just a sketch. We want to have the actual function with a function rule, right? We want to have the actual definition of V so that we could say at 1.5 days, we know what that accumulation is by the definition, right? So given its rate function R sub V, we want to be able to develop the actual function V, okay? All right, this is no small task. That's why it's going to take a couple weeks or 3 weeks, okay? This is no small task. So we'll take it a little bit at a time. All right, we have all the building blocks. Okay, so we have an idea what it looks like, but we don't know, right? The idea is we know the rate of change, and we're going to try to develop or build this amount. All right, so how does the statement R sub V of 0.7 equals 9.68 relate to the graph? What does that statement right there have to do with the graph of R sub V? So I should say R sub V. When you're given this whole graph, this red curve here, what does that expression right there have to do with that whole graph? Okay. What does it have to do with the displayed graph? What does it have to do? Is it just the rate of change? Yeah, or at 0.7 days. So this is what? One correspondence point on that graph. Ready? So at 0.7 days, and that's saying that R sub V of 0.7 equals 9.68 is represented on that graph as a correspondence point. When 0.7 days have gone by, we have 9.68 meters cubed in the ocean? No. The rate at that moment is 9.68 meters cubed per day. Okay, and that's what that correspondence points mean. Okay. At the moment, 0.7 days, the oil leaked at essentially a constant rate of 9.68 meters cubed per day. So now I'm going to zoom in on that moment. Okay, but I'm still looking at the rate graph. I'm going to zoom in on that moment. Okay, so here's that moment. I'm looking at the rate graph. So from 1.696 to 0.703 days. That's the same graph, just zoomed in, and then I changed the scale so it doesn't appear at the same slope, right? It doesn't appear at the same steepness. Okay, but what do we say about in a moment? In a moment, we think of what? Essentially a constant rate. What does a constant rate look like in a rate of change graph? Horizontal. So if we're going to assume we have essentially constant rate of change of 9.68 in this moment at 0.7, what is our assumption going to look like? It's going to look horizontal, right? Horizontal, because this is a rate graph. This is a rate graph. So if we're in the moment at 0.7 and we have this rate of 9.68, we're going to assume that it's 9.68, a constant rate for that whole moment. And that's okay. Why? Because the moment's really small. It's 6/1000th of a day. 6/1000th of a day. So compared to days, that's a really small amount of time. And so it's valid to say, okay, let's just, for this really small amount of time, this moment, assume a constant rate of that value 9.68. Does it make sense? Because constant rate of change on a rate graph is a horizontal line. Okay, well, now we've got constant rate of change. So the rate of change at the moment, 0.7, is constant at 9.68, represented by the blue graph. The blue display graph. All right, so now we've got a moment, we've got constant rate of change, so we can do everything we've learned. We can do everything we've learned. So suppose that the volume is at 0.7 is 13.15 meters cubed. So suppose we know that we're up to 0.7 days, the total accumulated amount is 13.15 meters cubed. But under our assumptions, what are dx, we're just going to do the first one here. What are dx and dv for finding v of 0.7013? And then I want you to find it. So what's dx? What's dv? And then what would V of 0.7013? This is all applying what we've already learned. It's just we're in a really small moment of time. But there's nothing new here. There's nothing new here. So what's dx? What's dv? For finding V of 0.7013, and then find it and then illustrate it. Let's see how it goes. Let's see how it goes. Just this first one, okay? Just this first one. Work together. Or think by yourself. So either, so think by yourself and then eventually work together. So, can we apply what we've learned? That's what we're doing. Nothing new here. Better than last semester. Yeah. 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 Okay. So here's the given correspondence point, right? So this is one point of that accumulation function that we're after, right? We're after the whole function, but we got this 1 point, 0.7, 13.15. And so if we want to find v of 0.7013, which is 701, so something about here. Okay, so we want to find what the volume is there. We start with what? dx. What is dx? Right, so we look at, so x final is the independent variable's value there, and x initial is the independent variable's value there. So dx is? Right, it's going to be final minus initial, or just how far you change from 0.7 to 0.7013. Lots of you got that, good. Okay, and then what are we assuming, right? We're over here, we're assuming, for this whole moment, we're assuming constant rate of change. So then we can get dv. What's dv? Or how would you express to get it? Right, so in this moment, we've got a constant rate of change of, what is it? 9.68. So we can take the 9.68 times our change in x. Will it fit? Yes. So dv is 9.68 times 0.0013. Did anyone actually get that value so I can make it accurate? Tell me. Go ahead. 0.0126. Okay, so it looks like it's going to put me right about here. Here's dv. And then we want, so now we want v of 0.7013, which will be what? The y coordinate of that point. And how will we get that? Right, so we've seen this before, right? This is like a y final, right? The final volume is going to be initial volume, which is 13.15 plus the change, which we said was, I'll just write dv. Okay, and that equals then 13.16. One more decimal place. 3. There it is. So we see that right here. 13.163 is about right there. So again, this is what calculus is about. Calculus is about applying the change in dependent is the change in independent times a constant rate in a very small moment. In a very small moment. Why? Because what happens when we get away from 0.7? So here's 0.8. Right? What happens at 0.8? A lower rate of change. So this applying the mathematics of constant rate of change is only going to apply in a very small moment around 0.7, like the one I picked. But then within that moment, we can use linearity. We can use that v final is v initial plus the change according to constant rate of change. Okay. So let's we'll do one more. So do this other one. So what about for 0.702? So now you'll go fast. You can do it. Second one. But going fast doesn't mean turn off your brain, right? Think about what you're doing. Think about what it all means. Don't just copy the procedure. What'd you get for DV? No? Something else? So what should it be? Okay. If you have a question about that, ask one of us on your way out. Homework will be up in about an hour.